Hello, everyone. It's Billy Younger again. I'm here to use Gauss's law to calculate the electric field on a non-uniformly charged, non-conducting sphere. So this is sort of the uh, me trying to make it as complicated as possible so you can see how the nuts and bolts work. Again, I will make use of spherical coordinates just in terms of talking about directions and using a vector that we know of. Not really any real actual use of a spherical coordinate in any sense. But anyways, the problem we're going to be solving, like I said, is a a sphere of radius r, charge capital Q, radius capital R, with a non-uniform charge distribution. Rho is equal to some constant delta times r to the 2 power, if I remember correctly. And we're going to basically use Gauss's law to compute the electric field inside. We're going to use Gauss's law to compute the electric field outside. And we're also going to determine what that constant delta is, as well as what its units are. Then for concreteness, I'm going to go ahead and evaluate it at very specific locations using very specific values of Q and radius. So let's get started. Let me start by sharing my screen with you so you can see the actual wording of the problem. So this is the wording of the problem. A non-conducting sphere of radius r has a total charge Q and a charge density given by rho times rho equals delta r squared. Delta is understood to be a constant. Use this information and Gauss's law to determine A, the value of the constant delta in units and its units, B, to compute the electric field for R less than R, C, to compute the electric field for R greater than R, and I think that's it for the main part. Now, for concreteness, I'm going to say once part A through C are computed, I want you to compute the numerical values of the electric field at half a meter. So that's halfway out from the center, since I'm going to make the radius to be R. 1.5 meters, 2 meters, and 2.5 meters. And I'm going to assume that R is 1.00 meters and that the total charge of the sphere is in fact 10 coulombs. That's a large charge, and it's going to result in a large electric field. We're currently using electric field units of newtons per coulomb, but it turns out they're equivalent to volts per meter, and we're going to get some really big values. So let me stop sharing this. I think everybody now has that. And as always, you can ask for the documents that I've used, as well as the documents that I write up by emailing me at billy@physicsolutions.com. That's billy at physics, there's an S in there, solutions, there's another S in there, and then an S on the end.com. So let's stop sharing the screen and let's go back to actually solving the problem. So I'm going to turn on my document cam. And I'm going to first off try to draw a sphere of radius r as well as I can without wasting any time to actually pull out a compass or anything. I'm going to make this my x-axis, this my y-axis, and this will be my z-axis. Doesn't really matter. The main thing is it's going to be concentric. That's a little bit out of focus. Let me get that better. There you go. And we're going to say the radius of the sphere is r, that's big R. And we're going to say the total charge is Q. And we know the charge density rho is equal to delta, which is a constant, times R squared. Okay, so that's the things we know. We know this is supposed to be a constant. Now, the first thing we're asked to do is determine the constant and its units, rho. Delta. So what I'm going to do is recall that the Q, the total charge, is either the integral of lambda times dl, or it's the integral of sigma times dA, that's the charge per unit length times the dl, or a charge per unit area times the dA, or like in this case, the charge per unit volume dV. Okay, I'm going to do this without triple or double integrals. So I'm going to use a spherical shell for my differential area element. And of course, the sphere has a surface area of 4 pi r squared. So if I make the shell dr thick, then you can roughly approximate the volume element dV to be 4 pi r squared dr. So let's go ahead and calculate that. I'm going to say delta times the integral of r squared. So this part right here is just the rho, delta times r squared. Now I'm going to put the dv, which is 4 pi r squared dr. And really that's about as easy as you can get on integrals. So 4 pi delta times the integral of r to the fourth dr, and I'm going to integrate from r equals 0 to big R. That's going to give me basically 4 pi delta r to the fifth over 5. So I can solve for delta if I so desire, and delta will in fact be equal to 5q over 4 pi r to the fifth. It's not as easy to see from there, but the units turn out to be coulombs per, well, actually it is pretty easy because the pi has no units, so the units turn out to be coulombs per meters to the fifth power. But you could also have gotten it from here. You know this has to be coulombs per cubic meter. So if this is coulombs per cubic meter and this is square meters, then this will be coulombs. Solving for density would be coulombs per meters to the fifth. So I write that as the units of delta are coulombs per meters to the fifth power. So that's another answer as well. Now, as you can tell, when we start to do Gauss's law for like r less than r, then we're going to have to find out what fraction of the charge is inside. So I'm first going to imagine a Gaussian surface because I'm going to use Gauss's law, and Gauss's law is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That's Gauss's law. We basically, to use Gauss's law the way we're using it here, which is to try to solve for this electric field by using symmetry, is we make a hypothesis of what E is, both magnitude and direction, and we choose a Gaussian surface symmetrically so that the electric field is perpendicular to and constant on the entire surface, or on the parts where that's not true, the electric field will literally be perpendicular to it so that the dot product will actually go to 0. This dA vector is a differential area element of the outside of the closed volume. That's what that circle's on there for. So it should point outward from the insides of the container. And therefore, on the cases where E is perpendicular to the surface and a constant, the E dot dA is just going to become E times dA because they're actually parallel. So that's sort of the nature of it. So you choose that, and then this integral ultimately just becomes a constant E times the integral of dA plus other terms that are usually 0, but you might even have a couple different sides, for instance, or a couple different surfaces that have E times A. That's the case, for instance, with a Gaussian pillbox surrounding a flat, infinitely large charged plate. And then the right-hand side is just computing the charge enclosed in that Gaussian surface. Set the two equal to each other, boom. You can solve for E of R or E of X or E of Y. So in this case, I'm going to draw a Gaussian surface, and it's going to be a concentric sphere. And it's going to be at a radius r less than big R, right there. So that's my Gaussian surface. Again, both of these are supposed to be spheres, but I'm just drawing them kind of freehanded, so it's not that good. So for r less than big R, and we'll find out later the difference between less than, or equal to. But anyways, what I'm going to say is the left-hand side of Gauss's law is the closed integral of E dot dA, where E is a vector and dA is a vector. I'm going to use the symmetry of the situation to realize, hey, this charge at a given radius is constant. So it's uniform over a given radius because of the nature of the function. So I still have a spherically symmetric charge distribution. So I suspect a spherically symmetric electric field. So I'm going to say the electric field is actually E depending on R, meaning how far out you are is all that really affects the magnitude of it. And I'm going to say it points radially outward, and this is where I use the spherical coordinates. I'm just going to say it's times r hat, where r hat's just a radially pointing outward spherical coordinate. So just knowing the existence of the spherical coordinates, which I do have a video for on my YouTube channel, just knowing that gives us a symbol we can use, and that makes life a little easier. The dA, on the other hand, is just going to be dA, the vector, is just equal to some magnitude dA times r hat. Now, in my spherical coordinates video, I work out what this dA is, but you're not ever going to have to do that. That's if you ever have to compute this left-hand side integral for Gauss's law, you're not using Gauss's law the way we want you to in this course. Okay, this course, we're just using it to sift out that electric field in there. So I'm going to put this in here now. And remember, I'm doing it over a closed surface. That's what this circle around the integral is. It's got to be over a closed surface so that it has a clear inside and outside. And then that way, there's no ambiguity about which way dA points, because if there's a clear inside and outside, you know dA points outside. So the left-hand side is going to become integral of E of R hat dot dA times R hat. And just this first integral, I'm going to carry it out a little bit to make sure everybody knows what we're doing. In reality here, remember the dot product is a linear operation, so I can actually pull the scalar parts out of it, and I can just say the integral of E of R dA times R hat dot R hat. And that's actually correct. And remember, the magnitude of any dot product, A dot B, or excuse me, the dot product is the magnitude of A times the magnitude of B times the cosine of the angle between them. Well, a hat vector is by definition 1 unit long, and I literally mean 1 unit, not 1 meter, not 1 Newton, not anything. It's just 1 unit. So we got 1 times 1, and of course they're parallel because they're the same vector. So we got times the cosine of 0, and the cosine of 0 is 1. So this part just becomes 1. And I'm not going to do this with all the other ones, but I probably will do it at least one time with each problem I solve. So this ends up becoming the integral over a surface of radius r. So I'm going to say sphere of radius r is the range of integration. But notice, since it's a fixed radius, this E of r is just going to be constant. So I can pull that out in front, and I have E of r times the integral dA. So the left-hand side really just becomes E of r times the integral of the differential area element, which should give the total area of the sphere, which is 4 pi r squared. That's it. That's as easy as it is, and that's the way all your Gauss's law problems are supposed to work out. If you're using it to compute the electric field, you should just get a E of r times some surface area. Sometimes it's called A. Sometimes it's called 2 pi r times L. Or sometimes it's called A and there's 2 terms, but either way, that's it. Now, the right-hand side is a little more complicated when you have a charge distribution, but I'm going to show you 2 ways, both of which are pretty straightforward. So the right-hand side of Gauss's law, notice how I'm doing this. I work out the left-hand side, then I work out the right-hand side, and then I set them equal to each other, and then solve for E of r. And because of my hypothesis, I can then say E is a vector. So the right-hand side is Q enclosed over epsilon naught, and we literally mean the charge enclosed in that Gaussian surface, which is a sphere of radius r concentric with the original one. So in principle, what you're thinking about doing is taking the integral of delta r squared times 4 pi r squared dr and dividing it by epsilon naught, but we've already done that. Okay, so since we've already done that in this first part, I'm not going to waste any time redoing it. I know the answer is going to become 4 pi over 5 times delta times whatever my range of integration is, which in this case is going to be from 0 to little r. So I'm just going to replace the big R here with a little r, and I can say finally 4 pi delta little r to the 5th over 5 epsilon naught. So I know that's the case, all right? But we also know that we were not given delta. I had to solve for delta, so I expect the answer to come back as Q, and it's a little more instructive to come back in terms of Q. So I'm going to replace this delta with what delta actually is. Again, I'm taking a lot more time to do this than really necessary. But that's because I want to make sure you understand all the parts. So the delta is going to be 5Q over 4 pi r to the 5th. Sorry about that getting really small. That's 5q over 4 pi r to the fifth. In other words, I just took that and stuck it in there. That 5 is going to cancel out with that pi. This 4 pi is going to cancel out with this 4 pi. Ultimately, all we're going to have is q over epsilon naught times r over r to the fifth. That's really what it is. Now, that works, and you could redo that integral all you wanted to, or you might do that integral one time. The main thing is you know that the mass per unit volume has a fixed value. So in principle, you could actually set Q over 4/3 pi r, little r that is, cubed, equal to or excuse me, yeah, equal to big Q over 4 pi 4 pi big RQ or r to the fifth, and solve for little q in terms of big Q. And I think what you see is you can actually get the same relationship, this r to the fifth over r to the fifth. Now I'm going to set the left-hand side equal to the right-hand side. And to do so, I'm just going to write E of r times 4 pi little r squared is equal to, now I'm going to write Q over epsilon naught times r to the fifth over big R to the fifth. And the reason why I broke them up is because I think you can see that this r squared over here is going to cancel out with that and leave a cubed. So I ultimately get, using my original hypothesis, which is the electric field is equal to E of r, which I can now solve for, times r hat. I'm going to say that the electric field is in fact equal to Q r to the third power, that's a little r to the third power, over 4 pi epsilon naught r to the fifth. Notice that works unit-wise strictly because these are both meters, so meters to the cubed over meters to the fifth gives me meters to the 2 in the bottom, which is a normal formula for Coulomb's law. R hat for the direction, that's equal to the E vector. And this is for r less than big R. So we've got an expression now. This is answer to part B. And we see that, in fact, the electric field goes like r cubed inside. So it actually increases. The electric field gets stronger and stronger as you get closer and closer to the outside. And that means that basically is because normally if there was just a point charge, it would fall like 1 over r squared. But the 1 over r squared falls by 1 over r squared, and the charge per unit per unit volume increases by r squared. So that effect really cancels out, and you end up getting that there's way more charge accumulating than you are accumulating distance from charge. So you end up getting a increasing function of r. So for r less than big R, the actual electric field increases. Now we're going to do for r greater than big R. And for this, we are still going to use another sphere, but it's going to be obviously outside of the sphere. So I'm going to use a Gaussian surface that is a sphere of radius r. In this case, r is bigger than big R. And I will go ahead like I did before and compute the left-hand side and then compute the right-hand side, which would be easy peasy because I was given the total amount of charge. And Q enclosed for this sphere is obviously the total charge. So I don't even have to do any integrals or fancy stuff like that. So the left-hand side is going to equal the closed integral of E dot dA, which is in fact just the integral, or it's just E of R times the integral of dA, which you've seen enough to call that E of R times 4 pi r squared. Again, what I used here was the same hypothesis, E of R. E is equal to E of R times R hat, and dA would be equal to dA times R hat. So all this first step is moot. You're just doing the same thing. So I actually get this whole first part is exactly the same, whether the sphere is inside or outside. The other part's a little different. The right-hand side of Gauss's law is Q enclosed over epsilon naught. That's E and C that I'm writing there. It's Q enclosed over epsilon naught. When the Gaussian surface is the large sphere that encloses the total sphere of charge, then that's just the total charge Q over epsilon naught. So I can say left-hand side equals right-hand side. And I will set E of R 4 pi R squared equal to Q over epsilon naught. And now I can make use of my hypothesis that E is equal to E of R times R. Solving for E of R, I get Q over 4 pi epsilon naught R squared. So E, I'll write it as a piecewise function now. E as a piecewise function is equal to, for R less than R, we got Q R cubed over 4 pi epsilon naught R to the fifth, and that's for R less than big R. Again, I'm going to say something about that in a second. And then for R greater than big R, I got Q, and there's an R hat here, by the way. I got Q over 4 pi epsilon naught R squared R hat. I did remember the R hat that time. And this is for R greater than big R. Now, here's the deal. If I plug in a big R for R here, you see what's going to happen. I will get big R cubed over big R squared. So it's just Q over 4 pi epsilon naught big R squared. So in fact, this electric field is continuous at that boundary. So we can say that for it. That is the actual piecewise function for the electric field. And in fact, if you graphed it, the electric field strength as a function of R, and you put the radius, let's say right here, then Q over 4 pi epsilon naught R, big R that is, squared, would be what you have at R equals big R. But for R less than big R, it's going to be a rapid function. It's going to be a R cubed, so it's going to go like this. And then for R greater than big R, it's going to fall off like 1 over R squared, which does this. So this side is proportional to R cubed, and this side is proportional to 1 over R squared. And you'd see, in fact, the maximum electric field occurs right at the surface, and that value would be Q over 4 pi epsilon naught R squared. So this is the answer to part C. Now, as far as parts, the other parts go, the E of 0.5 meters, you're just going to have to plug in. If it's less than R, you're going to plug in little r, or big R is equal to 1.00 meters, and little r is the value that we specified. So in case we specified 0.5, so I'd put 0.5 there, I'd cube it, multiply it by 10 coulombs, divide it by 4 pi, and then epsilon naught is 8.85 times 10 to the negative 12th. And then the big R, of course, is 1 meter. So I'll show you how to do that at least once, and then I'll just write down the answers. So E of 0.500 meters is going to be 10.0 coulombs. Looks like y'all can't see that. Okay, 10.000 coulombs times 0.500 meters. That's going to be cubed. All that will be divided by 4 pi times 8.85 times 10 to the negative 12th. And the units for that guy is coulomb squared per Newton meter squared. Remember, this would be in the denominator in Coulomb's law. That's why the newtons and the meter squared are in the denominator of this. And then times 1.00 meters raised to the fifth power in the denominator. So that's really what you're doing to calculate that. With my calculator, I computed that to be 11.24, carrying one extra digit. We should only have 3 sig figs here, times 10 to the ninth. So this is literally 11.24 billion newtons per coulomb, which, as I said, was the same thing as volts per meter. When you do the 1.50 meters, you're now outside. So all you have is 10 coulombs, 8.85 times 10 to the negative 12, and then 1.5 meters down here squared. So that ends up being E of 1.50 meters is equal to 39.96 times 10 to the 9th newtons per coulomb. E of 2.00 meters. Someone's getting ready to come in and make my dog bark. So it's 22.48, again, extra digit, times 10 to the 9th newtons per coulomb. And then finally, E of 2.5 gives me 14.39, again, extra digit, times 10 to the 9th newtons per coulomb. I hope that helps. That is the ultimate answer, 42. Have a good day, and I hope that helps you all better understand how to use Gauss's law and how to apply it to, some pretty complicated charge distributions.